Good evening everyone, good evening. I welcome you all again to NEET Elite. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone, yes. Just let me know in the chat box if I'm audible and visible to every single guy right here. Yeah. Good evening everyone, good evening. Good evening. So my screen is on this side. I can read your chats on this side. Okay, it's not in the front now. Okay. Hello Raj. Hi Vimal. Hi Devika. Hi Mickey. Hello Harsha. Welcome everyone. Welcome back to NEET Elite. Just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys or not. Yeah. Give me some green signal. Perfecto. I'm doing great, guys. I'm doing great. I'm doing wonderful. Hope you are doing the same, yeah? Perfect, guys. Just give me a second, we'll be starting, yeah? All right, so people, as you all must be knowing, it's going to be a fourth session from the chapter atomic structure, right? In the last session, if you remember, we talked about something called as Planck's quantum theory, right? We did some of the questions based on that theory. And I gave you the introduction about the photoelectric effect as well. And in the today's session, we are going to talk about that photoelectric effect in detail, right? Whatever questions are there in photoelectric effect, whatever graphs are there in photoelectric effect, everything will be done over here in this session, okay? Well, the timing has not changed, it's just for today. It is just for today. From tomorrow, I'll be taking at my time 10:30 a.m. in the morning, yeah? Okay, it's just for today. So people, before starting the session, the ones who do not know me, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher right here on this NEET Elite channel, yeah? And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. And do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this NEET Elite channel, yeah? Well, the next class for the atomic structure will be day after tomorrow, okay? Tomorrow it's going to be the session for NEET 2021 students, right? And day after tomorrow it's going to be the session for you guys again, right? So without wasting a lot of your time, let me know in the chat box if you guys are super duper excited about the session. Yes, let me know in the chat box. Let me know in the chat box. Let me know in the chat box. Priyam, quantum number will also come, but not now, maybe in the upcoming session, absolutely in the upcoming sessions. I mean, you'll have to wait for 2 more sessions. After that, quantum numbers will come, yeah? Quantum numbers, Schrodinger's equation, shapes of orbitals, everything will be done over here in detail, right? Perfect, guys. So this is something which we are going to discuss in the today's session, which is what we call as photoelectric effect, yeah? In the last session, I gave you the definition of photoelectric effect, if you remember, okay? All right, so let's get started with something which we call as photoelectric effect. Let me just give you the quick overview of all the things which we have discussed in the photoelectric effect in the last session. Okay, see guys, understand properly what I'm going to do. I'm simply going to take a glass tube over here, right? This is a glass tube, and in this glass tube, I'm going to keep a photosensitive metal, right? This is the photosensitive metal, if you remember. I used to do it. This is the photosensitive metal, right? Over here, I have got one more electrode. Yes, I'm connecting this metal rod over here with the negative terminal of the battery, and the other rod I'm connecting with the positive terminal of the battery. Yes, that rod which I'm connecting with the positive terminal of the battery will be definitely getting some positive charge on it, right? And that rod which will be connected to the negative terminal of the battery will absolutely get the negative charge on it, right? This is something which we already know, okay? Now people understand what is going to happen. If you talk about these photosensitive metals, right? Whenever the light of certain energy falls on the photosensitive elements, photosensitive metals, electrons are emitted from the surface. Electrons are ejected from the surface of the metal, right? For example, this is the photosensitive metal which I have over here. Now, there is some light radiation which is incident on it, right? When this light radiation will be incident on this metal rod over here, some of the electrons will leave, okay? Some of the electrons will be knocked out from this metal surface, right? And that knocking out of electrons from the metal surface, when the light of certain energy falls on its surface, this phenomenon is what we call as photoelectric effect, right? So if I want you guys to define the photoelectric effect, what is the photoelectric effect all about? It's simply the ejection, right? The ejection of the electrons from the surface of the metal when the light rays of certain energy falls on its surface. This phenomenon is what I call as photoelectric effect, right? And the electrons which will be coming out from this photosensitive metal, these electrons are what we call as, I hope you remember, these are what we call as photoelectrons, okay? The electrons which will be knocked out from the surface of the metal are what we call as photoelectrons, okay? Now people, at the same time, the electron which came out of it, the electron which came out of the surface of the metal, can I say that electron will be dragged by this positive charge towards itself, right? Can I say electrons which are being emitted from the surface of this metal, those electrons, those emitted electrons, those photoelectrons, those will be attracted by this rod over here which is carrying the positive charge, right? When this positively charged rod will attract these electrons towards itself, can I say there will be some directional movement of electrons? Yes, there will be some directional movement of electrons over here from cathode to anode, right? There will be the directional movement of electrons from cathode to anode. And this directional movement of charge, this directional movement of electrons, which seems to be coming from, which are actually coming from the cathode towards the anode, it leads to the generation of the photoelectric current, right? The current which gets generated when these photoelectrons all together move towards the anode, this directional moment of charge, this directional moment of electrons, it leads to the generation of the current, and that current is what I call as photoelectric current, right? That's something which I call as photoelectric current. So people, what is happening basically from this phenomenon, can I say electricity is generated, okay? Photoelectric current got generated, as simple as that, yeah? Okay, I'm sure it's clear to everyone. Yes? Now there are some things which you need to know about this photoelectric effect, which is very, very, very important. Okay, this was the general overview which I gave you in the last session as well, yeah? There are some things which you need to understand, which you need to remember about the photoelectric effect. Point number one. That's something which we have discussed in the last session as well. That's something which I call as work function. Work function, right? Or you call it as the threshold energy as well. You call it as the threshold energy as well. I hope you remember it. And this threshold energy work function is represented by the symbol phi. Okay. What is this threshold energy all about? Let me make you understand this threshold energy over here in detail. Yeah. Okay. Understand, guys. If I talk about this photosensitive metal, let's say this is the photosensitive metal which I've taken over here. Okay. This is the photosensitive metal which I've taken over here. Right. In this photosensitive metal, there will be some ions of the metal, absolutely. Okay. There will be some ions of the metal, which I'm calling as kernels as well, okay? You call these ions as kernels as well, right? And at the same time, there will be some electrons in between these kernels. There will be some electrons in between these kernels as well. Now, if I talk about one particular electron, let's say I'm talking about this particular electron, can I say this electron is held by this ion as well as this ion towards itself? Due to which I can say this electron is bound over here. This electron is bound over here. There is force of attraction between this electron and this metal ion, and at the same time there is the simultaneous force of attraction between this electron and this ion as well, yeah? Now people, if you want to take this electron out of the surface, you definitely have to break this force of attraction. You will have to break this force of attraction, then only you can take the electron out. The minimum energy, the minimum amount of energy that is required, the minimum amount of energy that is required to knock out the electron from the surface of the metal, that's something which I call as work function of the metal. That's something which I call as threshold energy. The minimum energy which is needed to knock out this electron, okay, from the surface of the metal, that's something which I call as work function of the metal, or we call it as the threshold energy as well. So people, if you want to remove the electron from the surface of the metal, minimum, you have to supply this much amount of energy, which is equal to work function. You have to supply the energy equal to work function, then only what can happen? Then only you can remove the electron from the surface, yeah? Okay, so remember first thing, the minimum amount of energy. I'm writing the definition, yeah? The minimum energy which is required to knock out the electrons from the surface of the metal, from the surface of the photosensitive metal, photosensitive metal is something which I call as work function of the metal, yeah? Okay. And remember, this work function, it is the characteristic of the metal. Every metal has got the different work function, okay? Every photosensitive metal has got the different work function over here. I'm sure this is clear to everyone, right? Now people, the amount of energy which I'm going to provide in order to knock out this electron, the amount of energy which I'm going to provide in order to knock out this electron, I'm providing that energy in the form of what? In the form of light. Yes, I'm providing this energy in order to knock out this electron. In order to knock out this electron, I'm providing the energy in the form of light, right? In the form of light. Okay. Yes. And remember, the minimum frequency of the photon, which should be there in order to knock out the electron, the minimum frequency of the photon in order to knock out the electron from the surface of the metal is what I call as threshold frequency. The minimum frequency of the photon which is required to knock out this electron from the surface of the metal, that's something which I call as threshold frequency. Let me write its definition as well. I'm sure it's clear till here, yeah? I'm writing the definition of the threshold frequency. Understand properly what I'm going to write, okay? I'm writing something, the minimum frequency which the photon should carry to knock out the electron from the surface of the photosensitive metal is what we call as threshold frequency. And people, this threshold frequency, it is represented by mu naught. This is the symbol by means of which we represent this threshold frequency over here, right? Okay, can you let me know in the chat box if it is clear to everyone? Yes. Can you let me know in the chat box if everything is clear till here? Just let me know with some thumbs ups. Right? Let me know fast. I'm looking at the screen only, yeah? Let me know fast if everything is clear till here. Okay. Now people, comes the actual stuff, yeah? Now comes the actual stuff. This is something which I've told you in the last session as well, yeah? Now comes the actual stuff. What is that actual stuff? Or before talking about the actual stuff, let me tell you this work function, which I'm representing by phi, it's directly proportional to what? It's directly proportional to the, or let me write this is something which I've told you in the last session, right? Okay, I'm directly writing the result. Work function is equal to h nu naught, or you can write it as work function is equal to h c divided by lambda naught. Okay, this is something which we have discussed in the last session, if you remember. I'm not going to explain this thing again, okay? Just remember this now. Yeah? Perfecto. Let's get to know the actual stuff over here, which is really, really very important, okay? For example, let me take the metal surface over here, from which I'm going to take the electron out, yeah? This is the metal surface which I've selected over here. This is the photosensitive metal surface. Okay, I'm going to take the electron out from this photosensitive metal surface over here. So what am I going to do? Let's assume this is the electron somewhere here, which is bound with kernels, right? I need to break the force of attraction between the electrons and the kernels, then only this electron will be coming out. So for that purpose, I need to supply the energy, and I'm supplying the energy in the form of light radiations, okay? Energy carried by the incident light radiation, I'm representing by EI. Energy carried by the incident light radiation I'm representing by EI, which will be simply equal to h nu, right? Now people, for example, I'm giving you some arbitrary values over here so that you can understand the concept. Let's assume in order to knock this electron out from the surface, I need to supply some 50 joules of energy, right? For example, this is the minimum amount of energy which I need to supply in the form of light to knock out this electron, right? And that minimum amount of energy which is required to knock out the electron from the surface, that's what I call as work function. So over here, for example, this 50 joules is the work function, yeah? This 50 joules is the work function, right? Let's say this is the light which is coming from here. Let's say energy carried by the light radiation over here, for example, it's equal to 80 joules, for example, okay? I am providing 80 joules of energy in the form of light, but minimum 50 joules is required to knock the electron out, yes, right? So people, can I say the 80 joules which I am providing, which is the energy of the incident radiation, okay? Out of this 80 joules, 50 joules of energy is needed to knock this electron out, okay? So 50 joules of energy, out of this 80 joules of energy, 50 joules of energy is needed for the work function, right? So 50 joules is the work function. So there will be some 30 joules of energy still left. That 30 joules of energy which is left in this case is used to impart the kinetic energy to this electron after removal. When the electron will be coming out, after that, the remaining 30 joules of energy is going to be used in order to impart kinetic energy to this electron, okay? This 30 joules of energy is imparted in the electron in the form of kinetic energy over here, right? I'm sure it's clear to everyone. People understand. See, 80 joules of energy I'm providing in the form of light. Out of 80 joules, 50 joules of energy is needed to take the electron out, which is a work function. There will be some 30 joules of energy left. That 30 joules of energy is taken by the electron when the electron will be coming out, okay? After that, that 30 joules of energy will be imparted to the electron in the form of its kinetic energy, right? As simple as that, okay? Right? Chinmay, cesium is the perfect example for that, okay? So people, I'm going to generalize the equation over here, which is what I call as photoelectric effect, photoelectric equation, sorry. I can say incident energy which I'm giving in the form of light radiation, okay, is equal to work function which I'm representing by phi plus the kinetic energy, the maximum kinetic energy which is imparted to the electron. Yes, as simple as that, right? Now if we generalize this equation a bit more over here, what I need to do, understand, EI is the energy which the incident radiation possesses, right? Which you all must be knowing now, that's equal to h nu, right? Where nu is the frequency of the light, of the incident light, yes, is equal to, what is phi over here? It is a work function. Work function, as we all know, that is h nu naught. What is nu naught over here? Nu naught is the threshold frequency, okay? And plus what? Plus kinetic energy maximum over here. This equation which I have over here, this is something which I call as photoelectric equation. This is something which I call as photoelectric equation, point number 1. Point number 2, I can do something like this as well. Maximum kinetic energy which is imparted to electron will be equal to h nu minus h nu naught. I can write it like this as well. Yes, absolutely. Now people, if I need to plot a curve between the kinetic energy of the electron, right, and the frequency, if I need to plot a curve between kinetic energy and frequency, what is going to be the nature of the curve over here? Very simple, understand properly. So what I'll be doing over here, I need to plot a curve between kinetic energy of the electron which is emitted from the surface, right, and the frequency. Yes, so the curve is going to be something like this, understand properly. This is, for example, your kinetic energy, the maximum kinetic energy which the electron has after the removal, versus what? Versus frequency. I'm plotting the kinetic energy along y-axis. Yes, I'm plotting the frequency along x-axis, right? So instead of this kinetic energy in the equation, I'll be writing y because I have plotted this kinetic energy along y-axis, absolutely. This frequency, I have plotted along x-axis, right? So this is your x. And before this x, what I'll be writing? I'll be writing m, and this is going to be minus times c. Y is equal to mx minus c. I hope you remember the nature of the curve for y is equal to mx minus c. What is it going to be? It's absolutely going to be a straight line, but will this straight line start from the origin? No way. It's not going to start from the origin because you have got the intercept over here and the sign of intercept is negative. That means the curve will start somewhere here. Somewhere here. And the slope of this is positive because m value over here is positive, right? Okay. So if I ask you what is the distance from the origin, this is the origin. What is the distance from the origin to the point from where the curve starts? That's something which I call as intercept, which is denoted by c, and c over here is simply h nu naught. This is the distance, h nu naught. Okay, and at the same time, if I ask you about the slope, slope means the value of m. What is the value of m over here? The value of m over here is simply h, so slope of this curve is actually equal to the h, yeah? Okay, as simple as that. This is the curve between the kinetic energy of the emitted electron versus the frequency, okay? Let me know in the chat box if everything is clear till here so that I can move on to the next point. Let me know fast. Absolutely, your slope is positive. Absolutely, your slope is positive. That's why angle is acute. Yeah? Let me know in the chat box if every single thing is clear till here. Let me know fast. Right? Perfect. Twinkle star, there will be some 4 more sessions or maybe 5 sessions from the same chapter. Okay. No, Abdul Hadi, nothing about the exam. Just wait for the update. Perfect, guys. Let's move on and let's talk about few more important things. Okay. The energy incident on the metal surface is what? Is used in 2 parts. Number 1, to eject the electron out of the surface of the metal in the form of work function, to provide kinetic energy to the ejected electron. This is something which I told you, right? Okay. Whatever incident radiation will be there on the metal surface, some part of it will be used to knock out the electron from the surface, and some part of that incident energy is used to impart kinetic energy to that electron which has came out. Yeah. Okay. So people, this was the equation. This was the equation which I wrote. H nu is equal to EI incident energy is equal to work function plus kinetic energy maximum, right? So H nu is equal to H nu naught plus kinetic energy maximum. You can write it in this form as well. H nu is C by lambda. So it becomes HC divided by lambda is equal to HC divided by lambda naught plus kinetic energy maximum. Or you get this equation. From this equation, you can plot a curve between kinetic energy versus the frequency, yeah? Okay, this is something which I told you right now. Yes? Perfecto. Now, some important points related to the photoelectric effect, okay? There are some important points which you need to remember. Remember, guys, in order to knock out one electron from the metal surface, 1 photon is enough. 1 photon is enough to knock out 1 electron, okay? 1 photon is enough to knock out 1 electron. Remember, let me make you understand like this. For example, this is the metal surface. Let me make you understand simply like this. Let's say this is the electron and this is 1 more electron. Let's say these 2 electrons I have to take out, okay? So in order to take these 2 electrons out, I need 2 photons. I need 2 photons, okay? Right? For example, let me give you a scenario like this. Or let's keep it simple. In order to remove 1 electron, I need 1 photon, okay? It's also called 1 electron, 1 photon emission, or you can call it as 1 photon, 1 electron emission as well, right? This photoelectric effect, let me tell you, it's called as 1 photon, it's called as 1 photon, 1 electron emission as well, okay? Remember, a single photon can never take 2 electrons out from the surface, yeah? That's very important, which you need to know, right? 1 photon is enough to take 1 electron out. Right? 2 photons cannot take 1 electron out. 1 photon can take 1 electron out. Right? 1 photon cannot take 2 electrons out. 1 photon will take only 1 electron out. There is no time lag between the striking of photon and the emission of photon. Right? Once a photon comes, once a photon whose energy is equal to, for example, work function, once that photon strikes the electron, at that time itself the electron emits. the electron gets emitted, okay? There is no lag in between. There is no time lag in between. There is no time lag between striking of photon and the emission of photon. For example, this is the photon which is coming from here, right? And this photon which is coming from here, it has got energy equal to the work function. It carries the energy equal to its work function. Once it strikes this electron, the electron at that time only gets emitted, okay? There is no time lag between the striking of photon and the emission of photon, as simple as that, okay? I'm sure it's again clear to you, right? Moving on, let's try to do a small question over here, okay? By means of which you'll get this concept clear. It's a very small, simple question. Let's try to solve it, yeah? Let's try to solve this question. Perfect. Raja, maybe I'll do it day after tomorrow, or let's see, I'll let you know about the schedule, yeah? I'll let you know about the schedule. Perfecto. If the work function of an arbitrary metal is 3.1 electron volts, okay? Work function, it's given to me as 3.1 electron volts. Correct? 3.1 electron volts. Then find its threshold wavelength. I need to calculate the value of lambda naught. And the maximum kinetic energy of the electron emitted when radiation of 300 nanometers strikes the metal. I need to calculate the maximum kinetic energy with which the electron moves after the emission, and at the same time the photon which is being emitted, the photon which is incident on the metal surface, its wavelength lambda, it's also given to me as 300 nanometer. Okay, all these data is given to me, and this is something which I need to calculate. First of all, talking about this work function phi, as you all must be knowing, phi is equal to hc divided by lambda naught, right? Phi is equal to hc divided by lambda naught. Few minutes back I told you, right? Okay, so lambda naught is simply going to be equal to hc divided by phi, correct? hc divided by phi, right? For example, I'm using the value of hc as 1240 electron volt nanometer. Okay, this is the value of hc which I used, right? And phi is given to me as 3.1 electron volts over here. This electron volt got cancelled, so you'll be getting the value of lambda naught from here as 1240 divided by 3.1 nanometers. This is the threshold wavelength which I was supposed to calculate, lambda naught. Point number one. Okay, what is the second thing which I need to calculate? That's going to be maximum kinetic energy which is imparted to the electron after the emission. For that, I'll be using the equation. What is my equation all about? As I told you in the beginning, incident energy is equal to work function plus kinetic energy maximum, right? Instead of this EI, I can write hc divided by lambda is equal to phi is given to me as 3.1 electron volts, okay, plus kinetic energy maximum I'm supposed to calculate, yeah? Kinetic energy maximum I'm supposed to calculate, okay? Now people, instead of this hc, what I'll be writing, instead of hc, I'll be again writing 1240 electron volt nanometer divided by lambda is also given to me as 300 nanometer. 300 nanometer is equal to what? 3.1 electron volts plus what? Plus kinetic energy of the emitted electron, which will be in electron volts as well, right? So nanometer gets cancelled out. So over here electron volt, over here electron volt. So the kinetic energy which you'll be getting from this equation, that will be also in electron volts over here. Yeah? Okay, as simple as that. You need to just you just need to solve this equation. You'll be getting the kinetic energy maximum over here, which I was supposed to calculate, right? I think only these two things were we were supposed to calculate, right? Lambda naught and kinetic energy maximum. So let me know in the chat box if it is clear to everyone. Yes. Let me know in the chat box if it is clear to everyone. Let me know fast. Let me know fast. As simple as that. This is. Hello, Niranjana. Let me know fast. No, Ritik, the classes will be there on the same time, 10:30 a.m. in the morning. It is just today I took the class at this time. Perfecto. Deepak, I take classes for JEE on VJE Enthuse channel, right? You can check it out tonight at 10:30 p.m. I'll be taking a live session for the JEE 2021 students, okay? Perfect, guys. So condition Conditions to show the photoelectric effect. What are the conditions? What are the conditions which must be satisfied? Then only photoelectric effect is going to happen. Yeah? Very simple. Remember, if the incident energy which I am giving in the form of light radiation, if the incident energy will be less than the work function, at that time photoelectric effect is not going to happen. Okay? Because I'm providing the incident energy, but I'm not providing that much of incident energy which is needed to remove the electron from the metal surface, right? Okay, so whenever you are providing the energy in the form of light radiation, if the energy of that incident radiation will be less than the work function, the electron is not going to get emitted. Okay, the electron is not ejected. Okay, so photoelectric effect is not going to happen at that time. Point number one. Or you can say something like this: if mu is less than mu naught, if the frequency of the photon, if the frequency carried by the photon is less than the threshold frequency, okay, if the frequency carried by the photon, if the frequency of the photon is less than the threshold frequency, at that time what is going to happen? At that time no photoelectric effect is going to happen, because the photon should have minimum frequency of mu naught. The photon should have minimum frequency of mu naught, then only photoelectric effect will happen. And if the photon will have frequency less than mu naught, at that time photoelectric effect is not going to happen. As simple as that, right? Okay. Yes. So one more thing. If the incident energy is greater than the work function, whenever the incident energy will be greater than the work function, at that time photoelectric effect will happen. Or you can say, whenever the frequency of the photon is greater than the threshold frequency, at that time definitely photoelectric effect is going to happen, right? As simple as that. Okay, these are the two conditions which you must remember. In short, remember, incident energy should be greater or equal to work function, then only photoelectric effect will happen. Okay, or remember it like this: the frequency of the photon should be greater or equal to threshold frequency, then only photoelectric effect is going to happen. Otherwise it's not. Okay, yeah, exactly. There is some sound coming, right? It is the inverter battery sound. Okay. It's not some time bomb or something. Yeah, right? Okay, let's move on then. Let's talk about a few more interesting things. Yeah, this question was, I think, asked in JEE 2011. Okay, this very simple question. Very simple question this is. See guys, how this sort of a question is solved. Understand properly. The work function of some metals is listed below. So you are given with the work function of certain metals, right? See guys, work function of lithium is given to us as 2.4 electron volts. So minimum of this much amount you have to supply to lithium, then only electron from its surface will emit. Work function of sodium is 2.3 electron volts. So minimum of this much energy you have to supply in the form of light radiation, then only electron will be ejected from the surface of the sodium. Similarly, in case of potassium, magnesium, and so on, right? So I'm given with the work function of different elements or different metals over here. Okay, the work function of the some metals is listed below. The number of metals which will show the photoelectric effect when light of 300 nanometer wavelength falls on the metal. So the energy possessed by the incident radiation will be simply equal to Hc divided by lambda. This is the energy possessed by the incident radiation. Hc value is simply going to be 1240 electron volt nanometer divided by lambda is given to me in nanometer only. It is 300 nanometer. Can you let me know what is the value coming out from here? Can you let me know what is the exact value which is coming from here? Can you let me know fast? What is the value which is coming from here? Let me know fast. It is 3 point what? 4 point what? 4.1 I guess something, yeah? Let me know fast what is the exact value which you are getting from here. It is 4.13. Yeah? It is 4.13 electron volts. So the energy which I'm providing in the form of light, that is 4.13 electron volts. Now you can check it out. You can check it out on your own. Which metal is going to show photoelectric effect? How much energy you are providing in the form of light? You are providing this much of energy in the form of light. How much energy is needed for lithium to knock out the electron from the surface? Only this much amount is needed. So lithium is going to show photoelectric effect. Only 2.3 electron volt energy is needed. This one is also going to show photoelectric effect. Only 2.2, this one also. Only 3.7, this one also. Over here, 4.8 electron volt minimum energy is needed to remove the electron. How much I am providing? 4.13. So the energy which I am providing is less than the threshold, is less than the work function. So over here, no photoelectric effect, no photoelectric effect, no photoelectric effect, right? Okay, so 1, 2, 3, 4. So only 4 metals are there which are going to show photoelectric effect in this case. The question was somewhere asked in 2011 JEE mains, right? Let me know in the chat box if it is clear till here. Very simple, correct? So there are 4 metals which are going to show photoelectric effect over here in this case, yeah? Erwin, you can go for N. Avasti for physical chemistry, organic Solomon Fried, and inorganic JD Lee. Yes? Perfecto. No, Deepak, everything. You can watch the organic chemistry lectures as well. I've already finished GOC, hydrocarbons is there, amines is there, right? Okay, perfect. Now talking about one more thing, that's what we call a stopping potential. What is the stopping potential all about? Exactly, Raj, exactly. Okay, so what is the stopping potential all about? See guys, let's understand its definition. Let's read its definition first, then I'll make you understand what this what this stopping potential is all about, yeah? See, the reverse potential applied to stop the most energetic photoelectron from reaching the anode is what I call a stopping potential. Understand properly what I'm going to say. If you remember your setup which I gave you in the beginning, if you remember, this was the glass tube, right? This was the glass tube, correct? Okay, over here you took a photosensitive metal which was acting as the electrode as well, okay? This side I used to connect with the positive terminal of the battery. This side I used to connect with the negative terminal of the battery, and this side I used to connect with the positive terminal of the battery. Yes, that side which I used to connect with the positive terminal of the battery, it used to get the positive charge, and I used to call this electrode as the anode, right? I used to call it as the anode, if you remember. Yeah? Now we will understand properly what I'm doing. Just leave this case aside. See, understand properly. This electrode will carry the negative charge. This electrode will carry the positive charge, correct? This is something which we know. Yeah? Okay. Now, for example, this is the light radiation which is falling on this metal surface. Okay, this light radiation is carrying some energy. For example, the electron is emitted. This is the electron which got emitted from here, correct? Now, this electron will be getting attracted by this positive charge on this metal over here, right? Due to which there will be some directional movement of electrons, right? And due to that directional movement of electrons, due to that directional movement of charge, definitely current is going to get generated over here, and that current is what I call as photoelectric current. Yes. Now people, if I change the polarity of the battery, see what is going to happen. Understand. Let's assume, see, this rod over here, it was connected with the positive plate. Now I'm changing the polarity of the battery. I'm doing it like this, positive, negative. Now can I say this rod over here will be getting negative charge, and this rod over here will be getting positive charge, okay? And the electron which got emitted over here, the electron which is emitted, can I say this electron will experience some repulsions from this rod because this rod now carries a negative charge? So what I did basically, I changed the polarity of the battery. Right? After changing the polarity of the battery, this rod, it got the negative charge, and the electron which it came out, this electron now experiences the repulsive force from this rod over here, correct? But the electron, it has got sufficient kinetic energy, it's still going forward. The electron has got, for example, the sufficient kinetic energy, so the electron is still going forward, okay? No doubt, electron is going forward, but at the same time, it's experiencing some repulsions from this rod as well, okay? Now, if I keep on increasing the voltage of this battery, can I say there will be a time when the movement of electron will completely stop, okay? Can I say there will be a time when the kinetic energy, when the total kinetic energy of this electron becomes equal to the potential energy of the electron? Can I say something like that? Understand what I'm saying again? See, this is the electron which is emitted from the surface when the energy fell on this metal surface, the electron came out, yeah, right? Now, what I did, I changed the polarity of the battery. This rod got the negative charge. No doubt, electron is moving forward, but at the same time, this negative charge on this rod, it is going to exert some repulsions on this electron, okay? Due to which there will be some obstruction in the flow of electrons, right? Due to which there will be some obstruction in the flow of electrons. Yes. Now, if I keep on increasing the voltage of the battery, can I say there will be a time when this electron will come to the rest, okay? See, the electron is coming, but at the same time, I'm increasing the voltage of the battery. That means I'm increasing the negative charge of the battery. There will be a time when this electron will come to rest, okay? At that point of time, as per your work energy theorem, can I say kinetic energy maximum of the electron will be equal to the potential energy of the electron, which will be equal to E multiplied by V naught. This V naught over here, this voltage of the battery, which the minimum voltage which I have to supply, such that electron comes to the rest after the emission, okay? That minimum potential is something which I call a stopping potential, okay? Or you can say in simpler words, that minimum voltage of the battery which I need to supply so that electron stops after the emission, okay? That's something which I call as stopping potential, okay? Right? And as per your work energy theorem, I must say kinetic energy of the electron would have got converted into what? Into the potential energy of the electron, then only the electron would have come into the rest, yeah? So people, if you remember your equation, that was incident energy is equal to phi plus what? Phi plus kinetic energy maximum. Now, instead of this kinetic energy maximum, I can write something like this. I can write EI is equal to phi plus E V naught, where V naught is the stopping potential of the battery over here, yeah? This is one more equation which you need to remember, yes? So people, understand one more thing. You can write it like this also, see. EI, which is the incident energy, which is equal to phi plus what? Phi plus E mu naught. Sorry, phi plus E V naught. V naught is the stopping potential, which I'm giving in order to stop the movement of electron after the emission. Yeah? So EI I can write as H nu. Phi I can write as H nu naught plus what? Plus E V naught. Okay? This is one of the equation which you can use. Yeah? You can create one more equation from this. H mu is C divided by lambda is equal to H. This is going to be C divided by lambda naught plus E V naught, right? This is one more equation which you can write. Okay? And already you know one equation. What was that? That used to be EI is equal to phi plus what? Phi plus kinetic energy maximum. This was one more equation, if you remember, correct? As simple as that. Yeah? Let's try to understand a few more things out of here from the stopping potential. See, the reverse voltage, it does work on the electrons to stop it, and from work energy theorem, I must say something like this, which I've already told you. Kinetic energy maximum becomes equal to the potential energy. That's why, guys, it's simple. See, when the electron started moving, at the same time electron was experiencing some repulsions. Electron was moving forward. See, I'll make you understand a bit more clear. The electron was moving forward, right? This was the negatively charged plate over here, right? The electron no doubt was increasing forward, but the electron was experiencing some repulsions, yeah? I was increasing the voltage of the battery. That means I was increasing the negative charge on this rod, due to which the repulsions experienced by the electron increased. And a time came when the entire kinetic energy of electron got converted into its potential energy, right? So that's what I wrote, if you remember. Okay, this is something which we know. Now let's try to plot a curve between mu naught and mu over here, right? It's not mu naught and mu, it's V naught versus mu, okay? V naught, it's V naught, it's not mu naught. It's stopping potential versus the frequency. Stopping potential, which I'm plotting along y-axis, and frequency along x-axis, right? For example, I'm using one of the equation over here. Which equation should I use? For example, I'm using this equation. Let me use this equation. I'm using the equation as H nu is equal to H nu naught plus E V naught, right? I can write something like this. E V naught is equal to H nu minus H nu naught, correct? Or I can write V naught is equal to H divided by E nu minus H divided by E nu naught. I can write it like this as well, okay? Now you will understand. What I can do over here is, see, I've plotted V naught along y-axis. I have plotted mu along x-axis. So this is going to be basically m, right? And this term over here is going to be what? This is going to be intercept c. This is going to be intercept c. And the sign over here will be minus. Y is equal to mx minus c. And nature of the curve is again going to be a straight line. Y is equal to mx minus c. It's going to be a straight line like this. But we will at the same time, the straight line won't be passing through the origin because you have got the intercept over here c. So the sign of the intercept is negative. That's why the curve is starting below the origin, right? So the distance from here to here is what I call as intercept, and intercept is denoted by c, and c, as you can see over here, it is h nu naught divided by e. And what about the slope of the curve? Slope of the curve is m. M is basically equal to h by e. M is basically equal to h by e, which is the slope of this curve over here, right? Yes? Let me know in the chat box if everything is clear till here. Let me know in the chat box fast. Let me know in the chat box fast. Let me know fast in the chat box if everything is clear till here so that I can move on. This is the question. This is the question on your screen. Give it a try. It's a very, very simple question. Understand. Light of wavelength 400 nanometer is incident on the metal with work function 2.3 electron volts. Calculate the stopping potential required. A very, very simple question, guys. Yeah. A very, very simple question. We know already EI, incident energy, is equal to phi, plus instead of kinetic energy maximum, I can write what? I can write EV naught. Okay. This is the equation which I got a few minutes back. Okay. So first of all, EI is the energy possessed by the incident light, which is going to be hc divided by lambda is equal. Phi is already given to me as 2.3 electron volts plus E V naught, correct? HC, instead of HC, I'm using 1240 electron volt nanometer divided by lambda is given to me as 400 nanometer, right? Is equal to 2.3 electron volts plus E V naught over here. This nanometer got cancelled. Yes. Okay. So people, over here you have got E over here, E over here, E cancelled out, right? Correct? As simple as that. So I can get the value of V naught from here. So first of all, let me calculate this value. This value will be approximately how much? 1240 divided by 400. How much it comes out to be? Can you let me know fast? Can you let me know fast? People are saying approximately it's coming out to be 1.34 volts. Is that? So people are saying it's coming, V naught is coming as 1.3 volts over here in total. Yeah. Okay. So V naught is the stopping potential. Yeah. So basically from here you will be getting 3 point something minus 2.3 will be coming out to be 1.3 volts, which is basically your stopping potential. So this much voltage you have to keep, this much voltage from the battery you have to supply in the reverse polarity form, then only the electron which comes out from the metal surface won't reach the negatively charged plate. Yeah. Okay. Alright Adi, I'll be doing that, no issues. Perfect guys. So let's talk about something called as intensity of light. Let's talk about something called as intensity of light. How do we define intensity of light? Intensity is nothing, it is the intensity in general I'm talking about, okay? Intensity is the energy incident per unit area per unit time, okay? On the metal surface, for example, intensity is defined as the energy which is incident on the surface per unit area per unit time. This is how we define the intensity of the light. Intensity of any radiation, I must say. In general, intensity is the energy incident per unit area on the surface in a unit time, right? Okay, and this energy which I'm giving to the surface in the form of light radiation, it is simply equal to NHC divided by lambda, right? NHC divided by lambda. Okay, and you have got A over here as well, and you have got T over here as well. So you can clearly say intensity of the radiation is equal, intensity of the light radiation is equal to NHC divided by lambda A multiplied by T. This is how we calculate the intensity of the light. As you can see over here, intensity, right? Okay, or let me not write it in lambda form, I can write it in this form as well. See guys, I can write it as, instead of E, I can write N H nu, right, divided by what? Divided by A multiplied by T. This is how you are going to write your intensity over here, intensity of the light. N represents the number of photons which are incident on the surface. H is the constant, nu is the frequency, right? This is area on which this is the area basically, right? And T is the time, you know it, correct? Now, as you can see over here, actually your intensity, it depends on number of photons as well as frequency. But over here, what we are going to do is, we are going to keep the frequency as a constant. We are going to keep the frequency. Whatever photon will be incident on the metal surface, the frequency of the photon will be kept constant. So I can say intensity depends on the number of photons only. Okay? So remember, your intensity, it depends on the number of photons. As the number of photons falling on the metal surface increases, I must say intensity increases. Intensity of the light increases. As the number of photons falling on what? As the number of photons falling on the metal surface decreases, you can clearly say intensity of the light decreases. As simple as that, right? And I told you, one electron is enough to remove one electron. People just give it a thought. If I'm increasing the intensity of the light, that means number of photons on the surface which are incident are increasing. If number of photons falling on the surface increases, since one photon is enough to take one electron out, so can I say number of photoelectrons will increase? Number of photoelectrons emitted will increase. And if the number of photoelectrons emitted increases, can I say photoelectric current will increase? Can I say photoelectric current will increase? So remember from now onwards, on increasing the intensity of the light, what is going to happen to the photoelectric current? Photoelectric current increases. As simple as that. Yeah? Perfecto. Wonderful. Okay, this is something which I told you. Your intensity depends on the number of photons. Okay, talking about something called as photoelectric current. How come we calculate the photoelectric current? Basically, current, it has got the simple formula, charge divided by time. Right? Okay, this Q corresponds to the charge carried by the emitted electrons, right? Which is equal to N multiplied by E, where N is the number of photoelectrons emitted and E is the charge carried by one electron which is emitted, divided by T. This is the simplest formula by means of which we can calculate the photoelectronic current, yeah? Perfect? All right, yes. So variation of kinetic energy, stopping potential and photo current over here. See guys, both kinetic energy and the stopping potential of the photoelectrons, it varies with the frequency of the incident light. And how come your kinetic energy and stopping potential varies with the frequency? Okay, I think we have already made it, but still I'm going to make it again for you. See, I'm going to plot a curve between kinetic energy of the photoelectron and the frequency of the incident light. Yeah, it's going to be like this. I hope you remember. We have made this curve like a few minutes back. This kinetic energy, this frequency, and this was the curve, right? What was the slope of this curve? Slope of this curve was equal to h. And what was the intercept of the curve over here? Intercept was basically h nu naught, right? Okay. Yes, Shubham, you can watch these. Perfect. The next one was between nu naught and nu, if you remember. The next one was between, V naught, which is the stopping potential, versus V. The curve was again like this, right? And people, the slope of this curve, it used to be, if you remember, a few minutes back, I have made this curve, it used to be h by e. And what about the intercept of this curve? Intercept of this curve, it's used to be h mu naught divided by what? Divided by e. As simple as that, right? Okay. So people, there is one more thing which you need to know. Kinetic energy of the photoelectron, it is independent of the intensity of the light. Kinetic energy of the photoelectron, the electron which is emitted from the metal surface, okay? Kinetic energy of that electron, it does not depend on the intensity of light. It depends on the frequency of the light, yeah? We saw that. Kinetic energy of the photoelectron versus frequency curve, you saw that. It varies linearly with the frequency. Kinetic energy of the photoelectron varies linearly with the frequency. If you increase the frequency of the light, kinetic energy of the electron will increase, right? Absolutely. And at the same time, stopping potential will also increase, yeah? So let me make it clear for you. If you increase, for example, let me make it like this. If you increase the frequency of the light, what is going to happen due to that? Number of photoelectrons are not going to emit. Number of photoelectrons emitted are not going to increase. Remember, if you increase the frequency of the light, energy carried by light will increase. Energy carried by light will increase. We know it. If you are increasing the frequency of the light, I can say kinetic energy imparted to the electron will be more. If kinetic energy imparted to the electron will be more, what will happen due to that? Will the number of photoelectrons increase? No. If the kinetic energy is increasing, you can say stopping potential will also increase, right? stopping potential will also increase, because you need to increase the voltage of the battery in the opposite polarity, then only you can stop the movement of the photoelectrons afterwards. Yeah. Similarly, if I increase the intensity of the light, that means you are increasing the number of photons. You are increasing the number of photons. So on increasing the number of photons, what will happen? Number of photoelectrons emitted will increase. Number of photoelectrons emitted will increase. And if number of photoelectrons emitted increases, what is going to happen due to that? Photoelectric current will increase, in short. Okay. Yes, this is something. These are two important conclusions, two important statements which you need to take a note of. Correct? And I'm sure it's clear to you. So kinetic energy versus intensity. Kinetic energy of the photoelectron, it is independent of the intensity. It only depends, kinetic energy of the photoelectron only depends on the frequency of the light, right? As simple as that. So people, with this, your photoelectric effect is over, right? In the next session, we'll be starting the Bohr's model, right? I hope you enjoyed this session. It was a very short and precise session, because in the last session only, I had given you the introduction of the photoelectric effect. The next session is going to be day after tomorrow. Day after tomorrow, it's going to be one of the most important sessions, which is going to be Bohr's model. That will happen in the morning, 10:30 a.m. Yeah. And people, at the same time, if you have not enrolled into the long-term batch yet, for the students who are right now in class 11th, if you have not enrolled in the long-term batch yet, do get enrolled in the long-term batch as soon as possible, right? Because the next batch is starting on 21st of June. Okay. The next batch, that is that today? Is the 21st June today? What is the date today, by the way? I do not remember. Yeah, the batch has started actually. The batch on the actual Vedantu platform, it has started today. So do get enrolled as soon as possible. You can take any of these plans out. Just give them a try for a month. If you are new to Vedantu platform, you have no idea how this Vedantu platform actually is from inside. Yes. So do one thing. Do take a plan for a month. If you think you are getting benefited, then go for the 2-year pro subscription. Yeah. And this much of amount, which is for the 2-year pro subscription, this much of amount, you're not supposed to pay in one go. You can pay this much of amount in EMI as well. And it's a complete package of 2 years. It's not just for a year. Okay. So do get enrolled as soon as possible. And while enrolling, do not forget to use the coupon code as WSPRO. There is one more link in the description box of the video. That's for the Telegram. Do click on the link, get added to the Telegram group, and stay updated about the classes. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. It was nice meeting you. So I'll see you guys day after tomorrow. Okay, and in the day after tomorrow session, we'll be doing the Bohr's theory, which is one of the most important theories from the chapter structure of atom. Yeah. So with this, I'll take a leave. I'll see you day after tomorrow. Till then, take care. Bye bye. God bless you all. Love you all. Take care, guys. Bye.